there are two options. One is to take exam on May 24th, as we discussed. Another option is to take exam on May 19th, then you're done with this class. But there is a catch. You have to come to the extra lecture on Tuesday at 4:30 p.m. because I'm canceling this class. Okay. So, which one do you prefer? Do you want to finish earlier, or do you want to finish later? Any preference on number one? No one likes number one. Any preference on number two? Jinghyun, you should have a preference. No, I mean, this wouldn't work for you, right? So you should like the first option. Okay, any opinion? Again, number one. Anyone like number one? You have to raise your hand, okay? This option is for you, actually. Okay, Randy. We are discussing, when we are going to, have a final. So one option is this, and the other option is that. Anyone who likes number two? Okay. Only one likes number one, number two? So it doesn't matter?
Actually, Tuesday.
This one. Oh, okay. So that wouldn't work then. How about today? 4:30 p.m. Do you have another lecture today as well? Okay. How about May 12th, which is Thursday? 17th. How about 12th? Or, okay. How about exam on Thursday afternoon? Then I'll give you a regular lecture until this May 19th, and then we can arrange a time for the exam in the afternoon, like 4:30 to 6:30 or something like that. Would that work? Any objection? Is it okay with you? Okay. 공식이. Class?
The class is final presentation, so I don't know when the class finishes.
Oh, I
the
see.
class started 2:30.
Oh.
But I don't know when the class.
Okay. Oh. Okay. Then let's go for this one at 9 a.m. And I'll give you final exam earlier or not. Okay, so final exam will be May 24th at 9 a.m. Okay. So probably I'll give you exam on Thursday, okay, afternoon for you. Okay. So last time I started to talk about group velocity. Mathematical definition of group velocity is derivative of frequency with respect to wave number k, and that's a group velocity. And the physical interpretation of group velocity is the speed of propagation of envelope. So these are the envelopes, and usually dispersive waves form a group to travel as a group. So this envelope, this is called the envelope. This envelope is propagating with the group velocity, although each phase is moving with the phase velocity c. Okay, and for group velocity, for the gravity waves, we learned that the phase velocity is greater than group velocity. Okay. So although each phase is traveling faster than the envelope, but the amplitude decays, so they cannot propagate, to another group. Okay. The reason why water waves form a groups is that the waves of different wavelengths travel with a different speed. And so in other words, since water waves are dispersive waves, and they form a group. And as I said last time, in reality, you don't have only one carrier wave, or carrier wave of one frequency. So this waves inside is carrier waves. So what you really see is this solid line, but you can imagine the envelope. But in reality, in real ocean, the carrier wave can have many different frequencies, and then you see something like I'm a little exaggerating. So here I have a relatively longer waves, and inside of this group I see relatively short waves, and long waves again, and that kind of thing. Okay. So when we take when we evaluate group velocity, we evaluate the first derivative at the carrier wave. Okay. That's how we evaluate the group velocity. And inside of this group, there is some carrier wave K1. The wave number of carrier wave is K1. Here, the wave number of carrier wave is K2 in this group, right? And obviously, K2 is greater than K1 because wavelength is shorter, which means this is a longer wave and these are the shorter waves. And in terms of group velocity, this group velocity is CG1, and let's say this is CG2, then which one is bigger? Long wave has a greater phase velocity and the group velocity. So this guy is bigger because wavelength is longer, therefore wave number is smaller. And so this group propagates faster than this, and then this guy will catch up, this group will catch up this group, and then later time you will see this group ahead of this group 2. Okay? So each group, different groups, collide, and then they pass each other. Okay? And that kind of process, repeat. So that's one of the interpretation of group velocity. The other interpretation of group velocity is the velocity at which wave energy propagates. That's where we were discussing. And the first I defined the mean energy density, which is energy per wavelength. Okay. And this is a summation of kinetic energy and potential energy. So this means I take average over one wavelength. So whenever I say this means I integrate it and then divide by 1 over lambda, okay, over dx, something dx. That's what I mean by that. And then when we plug in, substitute linear solutions for potential velocity potential, then what we learned is 1/2 rho g a squared. A is wave amplitude. So half of that came from potential energy, and half of that came from kinetic energy. And but anyway, so this is a total. So if this is one period, no. Okay, so this is a mean water level, and inside of this domain, total wave energy contained is 1/2 rho g a squared times lambda. Okay, total energy inside of this, because this is energy per wavelength. Of course, per width as well, because we are looking at two-dimensional problem. If you have the third dimension whose length is say w, then you have to multiply by w as well. Okay, now, so this is the energy per wavelength, and then what we really want to know is what happens if I have some domain. Doesn't have to be just exactly one period. I want to know how energy changes inside of this domain. Okay, so this domain is surrounded by free surface, and of course bottom. And let's say this is S1 and S2. So what I want to know is how this energy changes inside of this, the fluid domain. And to know that, I have to take a time derivative of definition of a total energy, which is so let me write down very general expression, and then I'll get the I'll write everything for this domain. So this time, this is a kinetic energy per unit volume, and this is a potential energy per volume, right? If I multiply by volume, then this is a mass times g times a the length distance. So that's a definitely potential energy. since the domain is fluctuating in time because free surface is moving in time, and therefore when I take a time derivative of that, I have to worry about time dependence of this quantity and also time dependence of this quantity as well. So we use Reynolds transport theorem. I think I talked about it earlier. There is a Reynolds transport theorem from which we can write this as time derivative of this guy right? So I just take a time derivative, like this is a constant, okay? And then I take a surface integral, surface boundary, which surrounds the volume V is and V dot N ds. So this is the normal velocity of the boundary. So time derivative of this quantity can be decomposed into two. One is the partial derivative of this guy with respect to time, and the other is the effect of the change of fluid volume, and that can be written as a surface integral of this. Okay, so that's a Reynolds transport theorem, and then what we have here is that this is independent of time, so I don't have to worry about it. And then I have V of t, and I just take a time derivative of that, and which is okay, because this is a grad phi dot grad phi, so I'm just taking time derivative of that. That's what I end up with. So this is that, and this is independent of time, so that will give us 0. And from here I can use Bernoulli equation, and therefore I have minus p or plus. So plus, right, minus p minus plus rho. Let me take a time derivative here. d phi dt, sorry. Same thing. And rho d phi dt. And v dot n ds over s. And this quantity can be rewritten as minus, this is chain rule, so the integrand can be written in this way, and therefore this integral, this guy is 0 because phi satisfies Laplace equation. Okay, so when I take gradient, I'll get this, so they will cancel out, and then when I acting this gradient on here, then this is exactly this, and then from here this guy goes vanishes because phi satisfies Laplace equation. Then bye bye, and then I end up with a volume integral of gradient of something, which I use Gauss theorem. So to change this as over in surface integral. Okay? So going from this, using this to this is Gauss theorem. So we use Gauss theorem. We've used it a few times before. And then I have P plus rho d phi dt b dot n ds. Okay? So finally, the rate of change, the rate of time, the time rate of change of energy inside of this volume is given by the last expression, d phi dt, d phi dn, ds. So this is d phi dn. And then I have a minus p plus d phi dn, d phi dt, and v dot n ds. This is this is S, not S of B. S. This has to be also S. So this is a normal fluid velocity on boundary S. And this is normal velocity of the boundary S. Okay. Now, let's start with the S bottom, which I call SB. What is this? V dot n. Bottom is flat, fixed, so it has to be 0. So V dot n is 0. What happens to d phi dn? Fluid velocity at the bottom. Also 0, because fluid cannot penetrate into the body. So both terms vanish on the bottom. Okay? What happened to S free surface? What is P on the free surface? 0. That's our dynamic free surface boundary condition. So free surface, this guy goes to 0. And then I look at this, and then I have this d phi dn minus v dot n, right? Because I have the same thing, d phi dt. What is this? That's a kinematic boundary condition. Normal velocity of fluid has to be the same as normal velocity of boundary. Okay? So that's a kinematic boundary condition which has to be 0. Rigid surface, what happens? D phi dn, if this guy is moving with some velocity v, then this is our kinematic boundary condition on the body, right? Normal velocity is 0. Free surface, we say df dt equal to 0, which means this is a material surface. So wherever the boundary moves, fluid particles on the boundary has to move with with the same normal velocity. Okay, otherwise, this condition cannot be satisfied. Boundary moves in this way, and fluid particles, it has to be moved in that way, in the normal direction. Otherwise, there is a gap, okay, which is not allowed. And therefore, this is a kinematic boundary condition. This is equivalent to this is exactly this. Or I can write in the following way. This is a velocity vector dot the gradient of phi dot n, which is I divided by 1 over square root of 1 plus zx squared is equal to, I move this guy to this way, and then I end up with this is grad of phi dot n. This is v dot n. This is v dot n. And this is n, normal vector. And this is grad of phi. So that's exactly, what it is. So what we end up with, P is 0, and this minus this is equal to 0. So there is no contribution from free surface. Okay. So when you look at how the energy changes here inside of this domain, bottom and free surface doesn't do anything. Doesn't add any energy or doesn't extract any energy out from this domain. Although free surface is fluctuating, in terms of energy, they don't do anything. Okay. So at the end, what I end up with, dE dt is equal to contribution from this boundary S1 and S2. That's the only contributions that I end up with. But over there, before I write that, on S1 and S2, V dot n, I fix my volume, the boundary, and V dot n is 0 because the boundary is not moving. Although fluid can go through, okay, I can fix this is a arbitrary boundary that I can fix. I can fix S1 and S2 here or here, but I don't move those boundaries, and therefore V dot n is 0, and therefore I end up with that's exactly the exact expression of dE dt. I think I forgot rho here. Sorry, but it's a constant. I forgot rho here. So put rho later. So rho here and rho here. And therefore, I have rho here. And then rho here. Okay. Yeah. Yeah. So I have rho here. And then dE dt is equal to S1. My normal is always away from the fluid domain. So these are the normal. And so the first one is minus rho d phi dt d phi dx ds over S1. And then I have rho because normal directions on S2 is opposite to normal direction on S1. So what it says here is, I can rewrite this as minus and minus. So this is this part. The quantity in the first bracket is exactly energy flux. How much energy is coming in to the domain through boundary S1. So energy flux in minus, this is energy flux out. Okay. So we went through, many steps, but at the end of the day, what we got is the following. If I want to know how energy changes inside of this fluid domain, what I have to count is energy flux through this boundary and energy flux through this boundary. Okay? If more energy comes in than energy going out, the more energy coming in, when more energy comes in than the energy that goes out, then the energy increases inside of this fluid domain. Okay, if energy flux on S2 is greater than energy flux S1, then it's a negative, meaning that energy decays. Okay, so energy flux is an important quantity that you have to measure if you want to know how energy changes inside of your fluid domain. So energy flux is defined by, let's call it F, is defined by minus rho minus H2 zeta and d phi dt d phi dx dz. That's the energy flux that we have. S1 goes from minus H to zeta. And once again, since we are interested in linear waves, this is already a second order quantity, and then we can replace zeta by 0. It's again linearization. And then we have a linear solution for phi. And then you substitute here. Okay, then you will get an energy flux over from minus H to mean water level. That's how much energy passes through this vertical stage, the cross section. Okay. In particular, if you measure the mean over one time period, so you fix the space, you just monitor how much flux is going in over one period, and then what you will find out is the following. I'm not going to go through that because I don't have time, but you can go through. And then this is exactly the expression. Okay. So when you substitute phi from linear theory. And then the flux over one period is exactly mean energy density times group velocity. Meaning that this energy is propagating with this speed. So group velocity is the speed at which energy propagates. So once again, we found the expression for energy flux at a given point or given the x location, and then we realized that if it changes in time because the free surface is fluctuating in time, right? Because waves are propagating, so free surface is fluctuating, but if you take the average over one wave period. And then you realize, how much energy is going in is this. So this is a mean energy density per wavelength times, group velocity, meaning that this much energy is propagating with this speed. Okay? And that's why I said that this group velocity is the speed at which energy propagates. When we derived this result, we didn't use the concept of envelope at all. Okay, so this is a completely independent, definition of group velocity. The first one is purely kinematic one. This is a more dynamical. Group velocity has a more dynamical, meaning. So as a consequence, when you look at soon, we are going to look at, wave structure interaction, right? And if this guy is moving with a speed u, you expect, waves, right, behind. But why don't you see, waves in front? Who said you cannot see the waves in front? Okay. The reason is group velocity is always then smaller than, let me put phase velocity. Okay? So, therefore, energy cannot propagate ahead of this guy. The energy is always, group velocity is smaller than this u, which is a phase velocity, okay, to see the steady state. And then, because, group velocity is smaller than phase velocity, that's why you always see, the waves behind the body. Okay. So this is a gravity wave. Of course, you see some little local effect in front of it, but you never see waves propagating here if you are far away from the body. Okay. Of course, when ship moves, you see disturbance in front of it, little bit here, but these are local. They decay exponentially fast. But if you are far away from the body, you never see any waves going, right? You always see waves behind. But capillary waves, which is typically less than 1.7 centimeter, due to the surface tension, you can see waves propagating ahead of the body, because in this case, for capillary waves, group velocity is greater than phase velocity. Okay, we didn't go through the expression for capillary waves, but that's what happens. If this is true, group velocity is greater than phase velocity, then you see waves in front of the moving body. So in a pond, if you see a little bug is moving, and then you see waves in front of the bug, okay? So which the reason is group velocity of those short waves that a bug generates. The wavelengths of those waves are pretty small. That's why group velocity is greater than phase velocity. So you see the waves in front of the body. Of course, here I see some local effect as well. So one important but obvious effect is if energy doesn't propagate, there will be no waves. Okay, and the waves are propagating with the group velocity. Okay, any question about group velocity? And we're going to use this group velocity a little later to discuss the damping due to the radiated waves when body is in motion. Okay. All right. If not, then this is our last the object the topic. So this is a special kind of fluid structure interaction. In any engineering disciplines, you always talk about in fluid structure interactions. But this is a very special fluid structure interaction because we have waves. Okay. In aeronautics or aerospace engineering, there is no wave structure interaction. Okay. In mechanical engineering, we don't have the wave structure interaction, but in ocean engineering, we do have the wave structure interaction. So quite often we see floating structures or submerged structures, doesn't matter. And then since we have free surface, that's a very special thing. We expect waves coming in. So this is incident waves. So for the last 3-4 lectures, I try to describe incident waves, how waves are propagating. Okay. And then what happens when incident waves are coming, and then there is some structure, so you expect some waves reflected. Okay, if you have a wall, then what happens? And waves if waves propagate toward the wall, then all the waves will propagate back. Okay? If I have a wall, so then I will have a total reflection. But this time, I have a submerged body or a floating body like this, and the depth of the body is not infinite. I have infinite fluid. So some energy will propagate, and some energy will reflect. So from here, I expect some waves will reflect. So I expect some reflected waves. And this reflected waves and incident waves will be there. And as I said, some waves will propagate. will be transmitted. So this is a transmitted wave. Okay. That's not it. Once waves approach to the body, this body starts to move. Okay, so this guy is going up and down, or moving, horizontally or vertically, or it'll do, rolling motion as well. And then, as soon as this body in motion, we expect, another wave going back, and these are the, radiated waves. By the motion of a body. So transmitted waves going this way. And radiated waves will propagate away from the body. Okay? So we have to describe all these waves. So that's why the problem is a little complicated. Okay? But the problem is really nonlinear, right? It's almost impossible to solve analytically, or it's impossible to solve analytically. So we have to rely on either numerical method, or we have to do linearization as before. Otherwise, we cannot solve it. Okay. So the reason why we can do linearization is the fact that we assume the incident waves are small. Okay. So that's a starting point. Since the amplitude of incident waves are small compared with the wavelength again, so let's say I represents incident waves. We assume this is much less than 1. Okay? Then we do the linearization. In other words, we linearize, free surface boundary condition and so on. By doing so, I can find, velocity potential phi. I can find, phi I from linear theory. Without linearization, I don't know what's coming. I cannot, describe, the incident waves. But with the linearization, I can describe phi I at least. Phi I, this is an incident wave part, right? Has nothing to do with the body. I'm assuming, far away from body, some waves are coming. I know what kind of waves are coming toward the body when I linearize, the problem. After that, since these waves are small, reflected waves and transmitted waves will be small as well. Okay, these waves are coming from these incident waves, and therefore the motion of the body is also small, unless the resonance occurs, right? So under that assumption, then the waves generated by the motion of the body will have a small amplitude. Okay, but the starting point is this: if this is not small, then motion cannot be small. Therefore, radiated waves wouldn't be small. Also, the reflected waves and transmitted waves will not be small. Okay, but if we assume incident waves are small, compared with amplitude of incident wave is small compared with the wavelength, then we can do the linearization. Okay, that's exactly what we do. And then we can formulate this problem in the following way. So under linearization, the problem I'm solving is Laplace equation again, because we assume fluid is ideal, inviscid, because we know if the Reynolds number is high, and incompressible water, and irrotational, because we start from the motion starts from the rest, and therefore we assume flow is irrotational, and therefore Laplace equation is the governing equation. And then we impose free surface boundary condition. That we discussed. So on the linearization, we do have this. This is free surface boundary condition. And then, since we have a body, so this is S sub B. Body surface. This time B is body. This is kinematic boundary condition that we talked about. And then we need some condition for at infinities. So if you are far away, no, this is not true. If you are far away from body, then you only have incident waves. Okay, so no. Let me just say radiation condition. So we need some condition at infinity, which I will specify later. And of course, gradient of phi goes to 0 as z goes to minus infinity, because we are looking at deep water. If it is a finite depth, then d phi dz goes to 0 at z equal to minus h. But at infinity, that's what we have. Now, how do we solve this problem? Okay. First of all, this boundary value problem, because I'm solving this governing equation with these boundary conditions. So this is a boundary value problem. But first notice this boundary value problem is a linear, because we linearize the problem. And therefore, I can write the solution phi as a linear superposition of incident waves plus whatever we do have, okay? Anything else there? So incident waves plus, I have to describe, incident wave, reflected wave, transmitted wave, and radiated waves. But I will call this phi I, and this phi prime represents all other waves. Okay, I can do this because the problem is linear. And then let's see. So I know what this is known. If I know wavelength and wave amplitude, I know how to write the phi I. That's what we discussed so far. Okay. So phi I is for example C times A times e to the kz cosine sine kx minus omega t. In deep water, otherwise, I have a hyperbolic cosine here. Okay. So that's a incident waves coming from minus infinity to infinity. So if waves are coming from right to left, I just change the sign here. So if I have a minus sign here, then my waves are traveling from left to right. So these are the incident waves. That is known. Okay. So I don't have to solve for phi I. All I have to solve for is phi prime. So let's substitute here into the boundary value problem. Then what happens? Right? Laplacian of phi I is 0. We solve Laplace equation to get phi I, right? So this guy is 0. So I end up with Laplace equation for phi prime again. When I did exactly the same thing for free surface boundary condition, at z equal to 0, of course. And then phi I already satisfies, free surface boundary condition. So I end up with okay. So free surface boundary condition for phi prime. So I didn't change anything so far. But if I look at the free body boundary condition, then there is some difference. Is equal to v dot n. Okay. So I end up with so this gives v dot n minus d phi I dn. And then radiation condition for phi prime and gradient of phi prime also goes to 0 as z goes to minus infinity. Okay. So all I did here is, I just wrote a boundary value problem for phi prime because I already know phi I. I don't have to solve it. Okay. And so I just rewrite the boundary value problem for phi prime, which I am trying to find. Now, so I have a Laplace equation for phi prime and the free surface boundary condition as well as before. And then I have a body boundary condition like this. Now I see two terms here. This is due to the motion of the body. Okay. And this is due to the incident waves. And now you can see the following. I further decompose phi prime into phi r and phi d. Okay. How do I do that? So let's say phi prime is phi r plus phi d. And then when I substitute this guy into the body boundary condition, and then I end up with this. Okay? And then I say my phi r satisfies, this is body boundary condition. My phi r satisfies this boundary condition. And my phi d satisfies okay? I can do that because this problem is linear. So I decompose phi prime into two parts. One satisfies, one body boundary condition. The other satisfies the other boundary condition. Okay? So that's another decomposition that I do. And once I do that, then I realize this problem is exactly radiation problem. If I solve, once again, when I do this composition, I don't change, the Laplace equation and free surface boundary condition. I still have a, Laplace equation boundary, free surface boundary condition for phi r and phi d, because this problem is linear. But the body boundary conditions are different for phi r and phi d. How? d phi dr, and the normal velocity of phi r is v dot n, meaning that you have free surface and Laplace equation, and then the body is moving with a certain velocity, certain normal velocity. So this time I don't have any incident waves. So let me write down the problem for phi r. So for phi r, I have a Laplace equation, and then I have a free surface boundary condition. Right? And then I have a body boundary condition given by this. So here, I don't see phi I. There's no incident waves. I have a body, and the body is moving with this normal velocity. Okay, so when body is moving, what happens? Waves are propagating away from the body. Those are the those waves are radiated waves. So here we are solving radiation problem. So this is a formulation for radiation problem. So for radiation problem, you forget incident waves. There's no incident waves, and it's very calm. And now the body starts to move with the prescribed velocity. So we pretend that we know how the body is moving, object structure or ships are moving, and then by solving this, I can represent radiated waves. So this is a radiation problem. And I said in a radiation condition, we need a radiation condition as well. And this time, radiation condition is nothing but waves, outgoing waves. So when body is moving, then waves have to propagate away from the body. When body is moving, waves cannot propagate into the body, right? Because this time, I don't have incident waves. if you don't impose this boundary condition, what happens is, this mathematically, you allow waves coming in and waves going out. Physically, waves coming in don't make any sense. So we have to choose mathematical solution which really represents, outgoing waves. So when body is moving, waves have to propagate away from the body. Okay? So that's the condition that we have to impose. And of course, we have to impose condition as z goes to infinity, minus infinity. On the other hand, for phi d, I can write similar boundary value problem. So phi d satisfies a Laplace equation, and then phi d satisfies the Fritzsche boundary condition. And then body boundary condition is minus d phi I dn on body surface. So this time, if you look at the body boundary condition, I don't have v dot n. Okay? Meaning that the body is stationary. But you have incident waves. So meaning that you describe reflected wave and transmitted waves. Those are the diffracted. So now you are describing here, in this problem, you're describing reflected and the transmitted waves. And here I'm describing radiated. Or radiating. Okay? So in this problem, if I draw problem, this is fixed, and I have incident waves are coming. Then I want to know what happens. That's exactly this problem. And this time, my body can move, but there's no incident waves. So waves are generated purely due to the motion of the body. This time, I fix the body, and waves are propagating, and then I see, what kind of force is acting on here. Okay? That's the difference between, the diffraction problem and radiative problem. But at the end of the day, my phi, total velocity potential, is phi I plus phi R plus phi D. That's a phi prime, right, before. So if I solve, this problem and that problem, then I will find the phi R and phi D, then I get a total velocity potential. The only difference between this problem and this problem is body boundary condition. You solve exactly the same, the Laplace equation. You're solving exactly the same, you're imposing exactly the same free surface boundary condition. The only difference between this and this is a body boundary condition. Okay, but physically, what you're solving is this problem here, and then some waves will be reflected and some waves will transmitted. But body is still not moving because I'm holding it. Okay? But this time, I don't have any incident waves. I just, move the body as prescribed, and then waves are propagated. So as you'll see later, the method to solve these two problems are identical. Okay, although the body boundary conditions are different. Okay, so we're going to use panel method again for this problem, and then Green's functions Green function will be the same. The only difference is when we try to find the strength of singularity, we impose the different body boundary conditions. Okay, so you'll see the details later. But my point is, the difference between diffraction problem and radiation problem lies on body boundary condition. Other than that, they are identical. Okay? So, conceptually, this problem has to be solved first, right? Because, you want to know how much force is applied when incident waves are coming. Okay? So you're holding it, and then waves are coming, and then you measure, force, and then you let it go. Okay? Then this is a problem. Okay? So since I know phi, I can compute hydrodynamic pressure. Of course, it's linearized. So hydrodynamic pressure is minus rho d phi dt. And of course, there are three components. Okay? I already know phi I. I'll find the phi d by solving diffraction problem. I'll find phi r by solving radiation problem. Okay? Once I know the hydrodynamic pressure, then I'll get the hydrodynamic force. By integrating hydrodynamic pressure over body surface after I multiply by normal vector. Okay? And now I put this guy. Minus rho is constant, so I can pull out from integral. This is a surface integral over body surface, wetted surface. And then I have a Okay. Quite often, this is a force that makes the body in motion, right? This is a force that makes the body move, and so this force is called wave exciting force. Okay, so this time I'm fixing it, and incident waves are coming. I'm measuring the force, and that force will make the body move. Therefore, this is wave exciting force. This part is due to the motion of the body, and as you will see later, this is related to added mass and damping. Okay. And also, if you only compute this, and then this force is called sometimes the fluid Kirchhoff force, but we'll discuss that later. Sometimes this part is more important than this part. Okay, and then we can neglect that, and then and the last thing is. In addition to the force, we have to compute moment as well. So the hydrodynamic moment is given by okay. So when we so this is P times the N, ds gives force, and then you multiply by the arm, and then we'll get the moment. So we'll discuss all this later, but and also I'm going to describe how you solve the diffraction problem and the radiation problem. But I hope you understand clearly what is diffraction problem and what is radiation problem. Okay, how we could decompose into two, and that should be clear to you. Okay. All right, then I'll continue to discuss this on Thursday.